Thank you very much. So you got a spoiler. So after the spoiler, let me start with a disclaimer. I've been in an endless number of talks of mathematicians promising that the talk is going to be easy and understandable by everybody, and the talk was probably not understandable, not even by the closest colleagues. So, am I going to be an exception to this? I don't know. But let me argue that somehow, whether the talk is enjoyable or not, in mathematics, is a disjoint fact from being understandable. Let me bring you an analogy. I have two great loves in my life. One is mathematics, and one is the girl that I married. Now, I understand very little of mathematics, and I have to say sometimes I understand even much less about my wife. I still love both of them anyway. So with that, let me start. The talk is going to be about three tales, and then some deeper mathematics. At least according to my intention, all you need to know to understand the concept in this talk is calculus and more variables. Okay, so how to take partial derivatives and how to integrate. Okay, so in the first tale, we start with Henri Poincare. And I mean, he's a famous physicist, and he actually wrote textbooks in calculus at the time. And he has this claim in one of his textbooks that a continuous curve might have a few jagged bits, but there would always be a few sections which are smooth. Or in other words, the theorem that you have a continuous function which is going from, say, the interval 0, 1 into R, so that continuous function is differentiable at some point. Now, it's a bit disputable whether at the time, the concept of function that they had is really like, what we have right now. Certain things weren't clarified, but it started being that way. So we start to be in a moment in which having a function is not anymore understood as having like a precise formula for making computations, as it was maybe 100 years before. OK, so Ampere publishes a proof of this. And actually, by the middle of the 19th century, almost every textbook quotes it. And apparently, even Gauss believed it. And the proof goes roughly in 2 parts. So the first is that if you have a continuous function, somewhere that function has to be monotone. Like, I don't know, monotone non-increasing or monotone non-decreasing, but monotone. And then a monotone function is actually differentiable at many points. And it's remarkable because the second statement is definitely correct and provable. It's a theorem in modern real analysis, and you probably see it in some courses. But the first one is questionable. And in fact, Riemann is the first who is known to be affirming privately to his students that he has a counterexample to that statement. And Weierstrass is the first one who actually publicly announces that he has a counterexample. I don't know why the picture is not appearing. Ah, here it is. OK. In fact, we know nowadays that Riemann's claim was incorrect, almost true. He had an example of a function which is continuous and very rarely differentiable, but there were actually a couple of points. There are a couple of points where you can prove, a few points where you can prove it is differentiable. The argument of Weierstrass is correct, and it's actually published not by him, by Dubois-Reymond in 1874, which is very interesting because Dubois-Reymond hears about this claim by Weierstrass, which was done at a conference. And he actually writes a letter to Weierstrass asking, like, hey, Karl, how the hell do you prove this, actually? So Weierstrass replies, and Dubois-Reymond publishes the proof, of course saying it's Weierstrass' proof. But as far as I know, the first recorded published version of the proof is actually by Dubois-Reymond. OK, it turns out that it was actually known before. So in 1920, Czech mathematicians discovered a manuscript with a correct proof, but a different example by Bernard Bolzano. It's very interesting. We study nowadays, theorems by Bolzano, Weierstrass, and so on. He's a very interesting character. So he's actually a Bohemian Catholic priest of at least half Italian origin. Bolzano is an Italian name. So I think his mother was German and his father was Italian. He's appointed to the chair of philosophy of religion in Prague in 1805, but he actually loses the chair in 1819 because of his political views. One of the things that he was saying, for instance, is that religion can't possibly justify a war. When the Austrian-Hungarian government discovered this, they told him, look, okay, maybe you restrict to mathematics, and maybe you do this somewhere else. And he couldn't actually publish even mathematics on mainstream journals. So that's also one of the reasons why this was only discovered later. Well, at any rate, this is a picture of, the Weierstrass function, of course, of an approximation of the Weierstrass function, because we can't really draw pictures of an actual continuous function on a computer where we just have pixels, right? And you see that one of the phenomena that intuitively happens, of course, is that this is essentially a function that shouldn't be monotone at any point. I mean, there's no, there's no interval in which it's going up or going down. It's always kind of, crazily or pretty fast varying at every small scale. Okay, so far so good. So these are some quotes from people at the time. So if Newton and Leibniz thought it possible, the differential calculus would never have been invented. Henri Poincare. An outrage against common sense, they are invented on purpose to show our ancestors' reasoning is at fault, and we shall never get anything more out of them. And actually, what David quoted, according to my research, is from Hermite, who said, I turn with terror and horror from this lamentable scourge. Okay, so now that's a very quick question. What do these three people have in common? They're French, exactly. Well, okay, it's a bad joke, actually, because Dubois-Reymond actually liked the result very much, and he was French, too. So, I don't know. What do we learn from this? Some French mathematicians are nice. Well, in 1827, the botanist Robert Brown discovers that particles of pollen in water move chaotically, right? So it's the Brownian motion, which nowadays we describe as a random walk, right? It's a walk at random, so at any time, we just are tossing a coin and going into a direction at random. Incidentally, a random walk gives you a continuous nowhere differentiable function. And this is how it looks like. I mean, it certainly intuitively should give you a continuous function which is on no interval monotone, right? Because if in that interval I'm monotone, I'm going up with probability 1 on that interval, okay? Which kind of defies the idea that you're going at random in different directions at any scale. Okay, so now let me get to the second tale. So let's say you are driving an old car, you are lost in the middle of some forest, and your mobile phone is dead, right? So of course, to go where you want to go, you need something which is very old-fashioned, which existed when I was a kid. I mean, nowadays you use a GPS, your mobile phone, whatever, but a road atlas. It's rare to see these things like nowadays. I mean, certainly my kids, I don't think they have an idea what we're talking about when we talk about the road atlas. Anyway, so what is a reasonable description of this object? So you have a collection of charts. Each chart marks the roads and maybe some other things like, I don't know, cities, mountains, rivers. But what's important for our discussion is that most road atlas actually mark the distance between cities on the roads. So they mark their length. So it's an information which is there. And then, of course, you might have noticed that different charts typically overlap, right? If you have a road atlas, which is, for instance, a book. Right? It's just like you're turning the page, and there is a little overlap, so that it's easier for you to get when you're getting to the boundary of the chart. And of course, you have a way to compare overlapping portion of the charts, right? So let me get to what we mathematicians call an abstract Riemannian manifold. So this is a mathematician's atlas. So you have a bit more precise descriptions of what these charts are, right? But in principle, they're just subsets of the two-dimensional plane, which are supposed to describe the geometry of a certain space, okay? So the global space is much more complicated than being like, a small subset or like a small disk, but you can cover it with a few of these disks, and you have a way of mapping portion of, what you're covering with one disk to another portion that you're covering with another disk if there is an overlap between the two covers. And that is what is called a differentiable structure, typically, because the mappings which are allowing you to kind of pass from one chart to the other is supposed to be differentiable. Okay, maps are not restricted to be two-dimensional. We could actually have an atlas of a three-dimensional world, for instance, or of an n-dimensional world too. There's a metric on it, so that is what we call a Riemannian metric. So this is a locally defined scalar product to measure the length of tangent vectors. Okay, so if you take a curve in this world, you want to actually, and you want to actually, like, you have a parameterization of this curve, which means you have a map. For instance, you can think that you're parameterizing with time if you're going through this curve with a car. So you have a map. Once you have a map, you can compute the vector, which gives you the velocity over that curve, and then you have a way to compute the length of, or like the absolute speed of that velocity, if you want, in the world. And so that you can actually measure the length of a curve, okay? So now, geographical maps are typically a distorted picture of the real landscape, right? So you very well know that. So maps are actually flat, but the correct landscape is corrugated. So what you actually see as, say, a mountain in real world on the map is just, squashed onto the two-dimensional space, right? So, in fact, the Earth is curved. So if you're trying to write down or to picture a global chart, you get actually something funky. For instance, Greenland looks as big as Brazil, right? So that's what happens. So here's Greenland. Here's Brazil. Now, when you actually go and look at data, the surface area of Greenland is like 1/4 of the surface area of Brazil. And the reason why that happens is because actually the Earth is a surface, is a sphere, and the way you're picturing your map is simply to project it onto a cylinder and then unwrap the cylinder into a square. And so whatever is actually up there close to the North Pole gets very distorted. There's no real way of dealing with it. Such type of distortion is due to the fact that the Earth is curved and your piece of paper is flat. Okay, so nonetheless, lengths which are written in the atlas correspond to the real ones. So even though what you're actually measuring on your atlas is wrong, you have a way to compute what is the distortion. So if you want, the Riemannian metric is that. So now, every imaginable Earth would have a road atlas, but here's a question which, it actually entertained mathematicians for a very long time. So is there something that you can imagine by just simply giving the charts and giving ways of comparing the length, which is kind of compatible with the rules that you find from charts, but you invent these numbers kind of at random, or you just imagine them, you give them. I mean, is it possible that you can realize that atlas from a physical Earth, right? So now let me go into more precise mathematical terms. So without annoying you, sigma g is a Riemannian manifold. So your sigma, you can think it's a piece of the classical Euclidean space, okay? But then you have this g, which is a tensor. So if you want, it's a matrix. And the matrix is going to give you the square length of a vector. So here you have a curve, gamma. So your gamma is some map which goes from, I say, the unit interval into your space. And the length of the curve in the Euclidean case would be the integral of the modulus of gamma dot, which is the square root of the scalar product of gamma dot with itself. Now, rather than having the scalar product of gamma dot with itself, you just have a general matrix over here, which is symmetric and positive definite, and that allows you to compute the length square of your vector, but it's changing from point to point, as you see, so it changes where you are, and it would be the Euclidean scalar product if Gij were a diagonal matrix with all entries equal to 1, okay? But it's just anything you might imagine. And here's the length of the usual Euclidean product, of the usual Euclidean curve, of course. And now the question that I was asking, whether any kind of imaginable atlas can actually be realized by an Earth, in mathematical terms can phrased in the following way. So do you have a mapping U from your space, which is a Euclidean space already, it's a portion of the Euclidean space, to some other space, which has maybe a different dimension. So think about this map, for instance, for the sphere to be just a parameterization of a portion of your sphere. So you can map a disk into the two-dimensional sphere, and if the two-dimensional sphere is the usual one, which is in the three-dimensional space, you are actually looking at the map from a two-dimensional space into the three-dimensional space. And now you want that this map is what mathematicians call an isometry. What is an isometry? An isometry is a length-preserving map. What is a length-preserving map? Well, it's pretty easy. So you look at any curve that you have in your initial space, gamma. You compute the length according to the rule that you're given over here. And that gives you a number. Now you look at the curve after I compose with the map U. So now I am actually in my Euclidean space. And now I compute the length in there by using the Euclidean scalar product. So it's the usual length. And I want these two numbers to match, no matter what gamma I choose. This is what would happen if you take a round two-dimensional sphere in R3, and you parameterize, I don't know, the upper half of the sphere with any map, and you compute what is the scalar product, which ends up being then the Euclidean scalar product after you apply the map. Okay? So down to earth, because after all, I just understand little more than taking derivatives. So I would have to go to my colleagues in geometry, actually, when I'm talking about fancy things like Riemannian manifolds. Down to earth, a guy like me writes down coordinates on the original guy, sigma, cranks out this metric, Gij, and writes down what it means for this map U in terms of differential calculus to actually make this magic, this isometry. And in differential calculus, it just means that it has to solve this system of partial differential equations. So the scalar product of the partial derivative of U in the coordinate I with the partial derivative of U in the coordinate j, these are two vectors in Rn, has to be equal to this Gij, to the ij entry of your matrix. And you see that there's a compatibility. Well, luckily, this guy is symmetric, and luckily, this guy does not depend on switching I and j. Okay? Very well. So in local coordinates, you have a continuous differentiable map, and this is if an isometry if and only if this happens. Very well. So here's the first theorem, which was proved by John Nash in the 50s. And he answered to this question by saying that, yes, under some very mild assumptions, which I'm not going to bother about, there are always isometric maps from your abstract atlas that you imagine is going to describe, I don't know, the roads of a certain imaginary world into a real classical Euclidean space, which is going to provide an isometry between your abstract Riemannian manifold and the portion of the Euclidean space that you're parameterizing. That looks fantastic. Only, in fact, not only that are isometric maps, there are always too many. So it's one of the situations in which, like, the answer comes disappointing because there are even many more things that you expected at the beginning, which, you know, ideally should make you happy, but in the end, it makes you unhappy because some of them are pretty weird. So here's a theorem that he proved. So for every n-dimensional compact Riemannian manifold, compact just means it's like, you know, finite. In the absence of any topological obstruction, forget about that. That is jargon for mathematicians to make this actually a correct theorem. So for instance, if you have a two-dimensional sphere, there's no problem of putting it into the three-dimensional space. But if you have some more complicated objects geometrically, then there are obstructions. But if you don't have obstructions coming from topology, which are kind of soft obstruction, then there is, in fact, always a continuously differentiable length-preserving map. And so far, you're very happy. But which does this additional thing? It puts all of sigma in an arbitrarily small ball. So now you should be very surprised by that, because it means the following. In principle, you should be able, because you see, this is a very nice Riemannian manifold. It's a two-dimensional flat space. And in principle, because of Nash theory, a Nash theorem, you should be able to put it in your pocket, which is a very small place, irrespectively of how big this is, without folding it, because it's continuously differentiable. I mean, we all know how to put it if we fold it, right? I mean, and we do this. That's all perfectly OK. But that's not allowed, because you have made actually this kind of edge over here, right? The map is not differentiable at this point, right? I mean, I have like one tangent, another tangent. That's not OK. So of course, all of us also know how to kind of compress a direction pretty efficiently by wrapping it up in a cylinder. And that's all OK, right? But now, how do I compress it in the other direction? And it seems impossible. In fact, not only it seems impossible, it is impossible. There is a theorem that tells you that a flat two-dimensional surface in R3, it's always a ruled surface. What it means to be a ruled surface, it means at any point there is a straight line which ends, there is a straight line passing through every point, which ends only when your sample ends. Of course, you could tell me, wait a minute, this thing actually contradicts Nash theorem, right? So because if I have a straight line which runs all the way, it's at least that long, I cannot put it in my pocket for sure. And the catch is that this other theorem needs more than one derivative to be proved. So notice that I said it's continuously differentiable. It needs two derivatives to be proved, or a little bit more than one derivative, actually, it turns out. Okay? So there's no contradiction. It tells you that it's a subtle question whether you want more regularity of your isometry. But it sounds like strange that you need actually more regularity, because, look at this partial differential equation, right? Look at this partial differential equation over here. Where do you see a second derivative of your function? So why would I need actually a second derivative of this function? I don't even need it to make sense, right? I'm just multiplying first derivatives. Well, anyway, let's leave it at that. So by this time, mathematicians got a bit smarter. So, it looks really ugly. And I'm pretty sure people like Chern would have liked to maybe make exactly the same comment as Hermite and the others. But in his math review, he says, well, this paper contains some surprising results. The embedded or inverse manifold is, of course, quite pathological. It's still interesting that, 50 years later, actually, there are applied mathematicians who have found that through not the theorem, but the way actually he proves the theorem, you can explain some very interesting phenomena in elasticity theory. For instance, the prediction of why it takes you a certain amount of energy to crumpling paper in a certain way. So these are two friends of mine, Sergio Conti and Francesco Maggi in 2005. OK, so let me actually get to the third tale. So this is something which is getting to the core of my research, which is the theory of the so-called differential inclusions. So in differential inclusions, you're looking at the following problem. So you have a map, U, and you're asking that your derivative u satisfies a certain restriction. For instance, what you can ask is that your derivative u belongs to a certain particular set K that you describe. Okay? It all sounds very abstract, but you all encountered an example of this, which is very famous, right? So take a map U, which is going from R2 into R2, an angle-preserving map, or what we call conformal map. Okay? It's a very famous object, which is heavily studied, used since the 19th century. What does it mean to be conformal? It means that the derivative of U, the 2x2 matrix that you get, satisfies the identity modulus of A squared is equal to 2 times the modulus of the determinant. Okay? Or in other words, it's a constant times a rotation. Up to sign of the determinant. Okay? So it sounds a bit unfamiliar maybe to some of you, but what does it mean? Well, conformal maps are either holomorphic or anti-holomorphic. Okay? So it's a good old holomorphic function, or a good old anti-holomorphic function. So if it is an anti-holomorphic function, just take the bar of the function. So nothing mysterious. In other words, what I'm telling you is that this thing over here, like, you know, this funky thing over here is just a strange way of rewriting the Cauchy-Riemann equation, or its cousin if you're looking at entire holomorphic maps. OK, so now let us look at the simplest situation. So let's say du of x belongs to k, and I'm just telling you that k consists of a finite number of values. OK, so here's an exercise. I mean, every math talk has an exercise, right? So consider two, well, it doesn't have to be 2 by 2 matrices. Let's say 2 times k matrices, A and B. And I ask you, where can you find actually a map which is continuous and which takes these two values, right? Well, the answer is pretty easy. The map exists if and only if this vector v, which is directing a line, is in the kernel of b minus a. Why? Because your function has to be continuous. So whether you come from the left or from the right, the trace of your function on this line has to be the same. And what is the slope on this line? It's just simply b times v if you come from the left, and it's a times v if you come from the right. And it has to match. And that is exactly what is written in this equation. OK, so now, of course, if you're looking at a map which is taking finitely many, whose derivative is taking finitely many values, the derivative cannot be continuous. So you might actually ask, what is the right category that I have to look at? Well, just believe me, the right category is what is called a Lipschitz map. So a Lipschitz map is a map such that the difference between the values at 2 points in absolute values bounded by a constant times the distance. OK, now here there's this beautiful theorem by Kirchheim and Price in 2003. So there are 5 2 by 2 matrices and a Lipschitz map from R2 to R2 such that the following happens. So you take AI minus AJ, and the determinant is always different from 0. The kernel is empty. So there's no compatible line which allows you to pass for a map to have one derivative here and one derivative there, OK? Between none of them. Nonetheless, there's a function which is Lipschitz whose derivative belongs to this A1, A5. So this function is never actually passing from one derivative to the other in a kind of like, you know, normal, sensible way. Because if there were an interface, you would have to have this compatibility condition. But the map still exists. And du, of course, is not constant. That's the important point. That's the catch. And it's not possible if you have 2, 3, or 4 values. OK? So now, this tale actually ends in the following way. Nash theorem is actually one instance of a general phenomena which is occurring in certain geometric problems. And it's the so-called lamentable principle, which was introduced by Gromov. Now, many tools were developed to prove theorems like the one of Kirchheim and Price in PDEs. And Müller and Schwerak in 1999 actually said, wait a second, so whatever the geometers were doing and whatever we analysts are doing, actually it's related. And there was a general tenet in early 2000 that, you know, this H principle is a mathematical curiosity. And there's even a speech at the Balzan Prize by Gromov which is saying that, you know, any sensitive math physics problem that you can imagine which leads to a partial differential equation, this H principle is useless for it. It shouldn't give you actually any information which is physically interesting. OK? OK, and I'm just going to tell you that that is not quite correct. So let me actually go to the second part of the talk. So the incompressible Euler equations. So these were equations which were written down by Euler 250 years ago, more than 250 years ago, to describe the motion of an ideal frictionless incompressible fluid. So here are the equations in all their glory. Okay. Now, what is this blue term? I've written it in components, but it's also what people often write in that way because V is divergence-free. You can just apply the Leibniz rule and pull off Vj, right, from that differentiation. Now, what do they mean physically? Okay, so the first equation is the balance of mass. It's like, you know, some right-wing dream, politician dream. You are at the boundary, and you know every immigrant which is coming should be balanced by somebody who's actually going away. So maybe better not to get any immigrant and, like, you know, stay all closed. So if you actually want, you just compute the flux of your vector fields across the boundary of your sample, and that integral has to be equal to 0. That is what it means that, you know, there's as many particles getting out as there are actually getting in. Now, if you integrate that by parts, and you have to know that this has to be true for every sample, you just get the divergence-free condition, the first equation. Okay? The second equation is actually the balancing of momentum. So here is the time derivative of the momentum for the fluid, which is actually sitting in the portion omega. And this momentum changes because of two reasons. So there are particles leaving, and so they leave with their own momentum, and particles entering with their own momentum, and that is the first term. But then there's a force which is exerted on the fluid element by the other portion of the fluids, and that is what is given by the pressure. Now, all of this is very nice, but, you know, do you see actually derivatives in the blue equations? You don't. I mean, the conservation of mass is something that you can actually write in an integral term, and the conservation of momentum is something that you can write in an integral term. Of course, you might object, well, the derivative is nice because, you know, it's a single packaged equation. Here, you would have to express this balance of momentum and mass for every omega, for every fluid element. So you have an infinite number of identities. Yeah, but the derivative, like, you know, it's a function equal to 0, the divergence v equals 0. And, well, this guy is just an infinite number of single equations, if you want, between numbers. So, you know, take your pick. Anyway, you can make sense if v and p are merely continuous of what it means to be a solution of the Euler equations. I mean, we mathematicians actually like a lot to do that, at least in my trade. And we call them weak solutions. So now here's a theorem. So this is what I proved actually in 2012 together with Laszlo Zekai-Hidi. There are continuous solutions which satisfy these balance laws. They are non-zero somewhere, but they are compactly supported in space and time. That is pretty weird, right? I mean, if they were an actual solution, which you would accept physically, these guys are at rest. Nobody is acting on them. And then at a certain point, they start moving, and then they stop moving when you're not looking at them, okay? Now, they don't sound like something that, you know, should exist, right? They were discovered for unbounded solution by Scheffer in 1993. So he was the first one to point out that this might happen. But his solutions were unbounded. They had finite, they didn't even have finite kinetic energy at each time. There was a second proof. Laszlo and I actually gave a proof that these can be bounded. And then at the time, we discovered that you can actually prove this as an H principle a la Gromov, a la differential inclusions, but exported into the realm of equations of fluid dynamics. Now, we also suggested, back then, with this H principle, you could actually prove a long-standing claim in the theory of fully developed turbulence. So now let me go to the Navier-Stokes equation. So in the Navier-Stokes equation, you actually augment your equation with a parabolic term. So this one now is a parameter nu, which is positive, and then you have the Laplacian. So these are very well-known equations. So for nu bigger than 0, you have the Navier-Stokes. For nu equal to 0, you have Euler, which you can think about as sort of limiting of the Navier-Stokes. If you have a classical solution and you multiply by v, scalar multiply, you can derive an identity. There is this ugly identity, which you can integrate in space and use a bit of calculus to derive this other identity. You need a little bit of assumptions on what is happening at infinity, but you know, if you don't want to discuss what is happening at infinity in your fluid, just say that you have something on the periodic torus. It's a mathematical idealization, but there is nothing surprising over here. Well, one thing which is surprising is that I dropped a factor 1/2, so you might notice that I didn't copy it over here. That's wrong. But this is just telling you that the time derivative of the kinetic energy, of the total kinetic energy of the fluid, is dissipated by the friction, right? You notice that if nu is equal to 0, there's no friction, the total kinetic energy is conserved. But then you can't have a solution which is equal to 0 sometime back, and then all of a sudden has positive energy. That can't happen, right? So what is the catch over here? Did I prove a wrong theorem? Well, possibly. Sometimes it does happen to me that I prove a wrong theorem, but I don't think this theorem is wrong. The catch is that it's a classical solution. To carry on this computation, you need derivatives. And my solution doesn't have derivative. It's continuous, but you know, it's very messy. Well, now let us look at actually what happens at large Reynolds numbers. So, you know, what was new before now has become epsilon. And the reason why it has become epsilon is because I'm suggesting that it might be very small. Now, there's a tenet in the theory of fully developed turbulence laid down by Kolmogorov, which actually says that this dissipation rate, even though you have this epsilon which is in front, which would suggest that when you let it go to 0, somehow that quantity goes to 0. If you look at typical solutions of Navier-Stokes with small epsilon or with large Reynolds number, if you have fixed somehow the macroscopic scale of the flow, actually that dissipation should stay finite. Okay? So you might wonder with which kind of convention do I show you pictures of people? I show you only pictures of mathematicians who died. So here, just Kolmogorov. Okay. Now, who cares about weak solutions? So just think about the following. Ideally, you would have a sequence, at least sometimes, of solutions of these Navier-Stokes equations with viscosity going down to 0, so with high Reynolds number, which are non-trivially dissipating energy. And non-trivially means I might actually make them dissipate a lot of energy if I inject in the initial data a lot of oscillations. But they should not be doing this. So they start from an initial data which is OK, maybe the same initial data for all of them, or maybe you vary the initial data but in a compact subset of the L2 space. So here it goes my claim that I was only using calculus. I'm using a little bit of functional analysis. And nonetheless, there is dissipation. So we don't know of any single example of what is this happening. But I can tell you that if when you send viscosity to 0, these guys converge to a reasonable solution of the Euler equation conserves the energy in the limit. So we should be converging either to a solution which does not preserve the energy, so to one of strange solution, or you should not be converging to the Euler equations at all. Okay? One of the two alternatives. We're not the first ones to actually think about this. So in fact, in a famous paper, which was published in 1949, Lars von Zager re-derived Kolmogorov's theorem independently. And he explored the possibility of setting epsilon equal to 0 and developed a theory of ideal turbulence. And in doing so, he advanced a remarkable conjecture. So he said, well, look, I might have continuous solutions of the Euler equations, but let me quantify what is the modulus of continuity. So you remember I showed you Lipschitz maps. So these are like what they're called Hölder maps, in which this alpha, this exponent, is allowed to be anything between 0 and 1. Okay? So above the threshold 1/3, such solutions should conserve the energy. And below the threshold, there should be solutions which don't conserve the energy. Of course, you could say, like, wait a second. What did he mean by a solution that does not conserve the energy? It was actually pretty precise. So he gave a very precise and rigorous definition by expansion in Fourier series, which happens to be equivalent to the definition I gave you if you just have continuous functions. Okay? So mine is just a reformulation, which at the intuitive level tells you why you can bother only of having continuous function. If you write down the Fourier series, what you're bothered about is the convergence of the Fourier series in a certain sense. And you will see that, for instance, L2 is more than enough. OK, so part A of the conjecture was proved by Eying and Konstantin A. and Titi in 1993. Concerning part B, Scheffer's example is the first rigorous instance. And we suggested a program to attack this part B in our paper in 2012. And this program was actually completed 5 years later by Phil Isett after a series of progress on the Hölder regularity of these solutions. So we got closer and closer to this threshold 1/3. I, some collaborators, Phil, and here's the whole number of people that you can cite. OK. So, and then actually, two PhD students of mine in 2023, just this year, have given a much, much simpler proof, actually, of that, which was a fairly complicated theorem. OK, so how do these solutions look like? Well, they're continuous, but they can actually be approximated by classical smooth solutions in which you have a right-hand side. And the right-hand side is becoming smaller and smaller as your parameter q goes to infinity. Now, ideally, I would like to have this right-hand side to really, really, really be the Laplacian of vq times a small number. And then I have my example with Navier-Stokes solutions, which are smooth. Of course, I'm not able to do that. And we are extremely far from being able to do that. But this tensor RQ, which is called R suggestively of a Reynolds stress, which is something which exists in the literature in fluid dynamics, is a way to measure how distant you are from a true solution of Euler. Okay? Converges to 0. So there's some key ideas, and the key ideas is that I am generating this sequence by correcting each time the previous solution by making, hopefully, this RQ smaller. So I start with what I get, and I want to generate the next member in the sequence in which this RQ becomes smaller. And I do this by adding a lot of oscillatory, a highly oscillatory perturbation. Okay, the building blocks of these are stationary solution of Euler. I don't want to go into that. And they are highly periodized, and they are approximately transported along the flow VQ. I just want to give you an idea of the proof. So I want to give you an idea of the proof on a very simple problem. The simple problem is the following. So I'm trying to solve another PDE, which looks much easier. I'm trying to find a function which goes from omega to r, which has modulus of the gradient exactly equal to 1. It's way simpler than the Euler equations, and there's no reason to go through this crazy way of solving it. There are much better ways of solving it, but it's suggestive of what I actually do in the Euler equation, which is too complicated to explain without going into a lot of PDE jargon or a lot of mathematics. Okay? So I start from a smooth map, phi 0. And I start from a map which has the following inequality. For instance, the map could be 0, identically 0. So it's important that the gradient doesn't go above 1. Okay, and now I want to produce an iteration scheme. So I produce from phi 0, I produce phi 1, from phi 1, I produce phi 2, and so on. I produce a sequence with the following goal. So along the sequence, I'm always a nice smooth function. I'm always with the gradient, which is strictly below 1. But I want to get closer and closer to 1. And the way I want to get closer and closer to 1, I want to compute the difference between 1 and the modulus of the gradient, but integrated, so in mean. And I want this to improve by a factor beta, which is less than 1, right? So of course, if I'm able to do this at each step, this integral is going down like a power, okay? And so it's converging to 0. Now, if I were able to prove that this function phi k is converging sensibly to a limit, which will be a byproduct of the way I actually produce it, then the final guy, hopefully, solves the equation. Because that integral has to vanish, and I will have the inequality that 1 is bigger or equal than the modulus. So it has to be equal to 1, at least on a set of full measure. Okay? So how do I produce my function phi k plus 1 from the function phi k? That's all I want to tell you. You can forget about all the history of the problem before. I'm just at step k, and I want to produce phi k plus 1. Well, first of all, phi k is very smooth. So if I concentrate on a very tiny region over here, right, I can just think that my gradient is approximately constant over here. So it's approximately a fine function, okay? And I magnify this over here just because I want to show you a picture, okay? So now, I am an affine function over there, and I want to perturb it to be closer to 1 in modulus, right, in slope. What would I do? Well, I could do a zigzag, right, in which the slope is exactly equal to 1. But if I do a zigzag, I'm not happy because the zigzag is not smooth. So I will do a nice, mild perturbation, which is kind of smooth, but it gets me much, much closer to have slope 1. So there is a portion in which I have slope 0, but that transition will be very, very fast, so that it doesn't count when I integrate, okay? Now, in formula, I'm just doing the following. I'm taking my function phi of x, and I'm adding a high oscillation, right? So this is the oscillatory function, so 1 over lambda p of lambda x. But then remember, this fact, that slope, is only valid in this tiny dot, right? So I have to cut off my perturbation outside of that tiny dot, because if I'm going over here, instead of being directly with this slope, I'm maybe directed with that slope. And if I add a zigzag in this way, where the slope is wrong, it's a disaster, okay? So that's why I have the cutoff. Okay, and now I just carry on computations. I compute the gradient, right? So when I compute the gradient, This is what I like, right? So I differentiate p, and there's a lambda coming out, and it simplifies with the denominator. And then I get an error because I might be differentiating the cutoff. And then I have a error, but look, the error has this lambda at the denominator. So I choose lambda huge. And that error doesn't bother me. Okay? So the improvement pushes the slope towards 1. The error pushes it maybe a little bit lower, a little bit higher, but it's a negligible error. And, well, I just have to be careful, not get me exactly to 1 with the improvement, because then the error might push me above 1. I don't want to do that, because if my slope gets above 1, I can't perturb it down to be closer to 1. Okay? So that's actually the convexity, which sort of, if you heard the jargon in this thing, this type of argument is called convex integration. So that is a situation in which you can see what the convexity is doing for you. Once you actually exceed slope 1, you can't go back. Okay? Now, well, cover your space with a lot of these disks and make your perturbation. Maybe you leave a portion of the space out, but who cares? I just want to improve that my integral being 1 minus the modulus of the gradient by, I don't know, 1 over a billion. So I just need to cover a substantial portion of my space, which I can certainly do. Okay. And, well, now you have to actually bother about the fact that you're converging. And what is the reason why you're actually converging nicely? Well, because if you think about it in terms of adding oscillations, it's like you're looking at a very lacunary Fourier series. Okay? Not really Fourier series, because you're modulating by these cutoffs, but you're looking at something which is very lacunary. So when you're adding your oscillations, your next oscillations are much higher than the previous ones. So they can't cancel. So there's an L2 convergence at the level of the gradients, essentially. Okay? Does this remind you of something? Well, look at the formula for the Weierstrass function. What is the Weierstrass function doing? Well, this is the formula. You have a parameter b and a parameter a. A is a small number. B is another number, bigger than 1. So you're adding actually a very lacunary Fourier series, which has a factor which is a to the n in front. So you take a, say, equal to 1/2, and the Fourier series is converging very fast. But when you actually differentiate, you have to the b to the power n, which is coming out. And that can actually compensate for the convergence, for instance, make explode, and the derivatives is not converging nicely. Now, that doesn't prove you that you are non-differentiable. Well, that I leave it to you as an exercise. If you actually take a and b appropriately, then w is continuous, but the difference quotient actually converges to infinity everywhere. So there's no way that this guy is going to be differentiable. And with that, thank you very much for your attention.
Thank you for that delightful tour of the terror of non-differentiability. And we have time for some questions.
You said nature actually produces that kind of thing. Could you give an example? Did you mean Brownian motion?
Okay, so no, I didn't say nature produces that kind of thing. No. I don't understand nature. I understand nature even less than my wife and less than mathematics. So what I'm saying is that in a mathematical idealization, it can be useful to introduce an object like the Brownian motion to compute certain things. Of course, at the level of nature, well, there's going to be molecules at a certain point. The thing is discrete. So there's a bazillion of molecules which are doing stuff. But, of course, with that point of view, you wouldn't study any continuum physics and always say oh, let us go back to quantum mechanics for each single molecule. But as an idealization, to extract certain type of information is still useful to actually think that you have a fluid solving a certain type of partial differential equation. At that level, it's certainly useful for idealization to think that. Well, when you have really it's really okay, the random walk, you think okay, I have a billion of steps, and each time I'm flipping the coin, and each time I'm going up and down with probability 1/2. But there's a useful limit to this process, and this useful limit to this process is a function which is continuous and nowhere differentiable, where you can put the probability measure in the space of, and so on and so forth. So it's certainly useful to have that. at least, quite a few mathematicians get a salary and families eat something out of that, I could say, if I want to be cynical. But beyond that, I do believe there's some value in doing this. So is there a value on doing convex integration for, say, proving that Onsager is actually right in his own claim about the solution of the ordered equations? Well, I'm not claiming that we do understand sort of the theory of turbulence in that way. But I can tell you that I can prove a specific claim, right? I mean, if that claim had been wrong, it would have been a sign that there's something in the intuition of Onsager which is wrong. But the claim is correct, and I can give you an actual proof.
What was Bolzano's example?
I don't know. I didn't actually look it up. Sorry, I'm not able to answer that. I didn't have time to look that up. I don't know actually if there's a translation. It's in Czech, I believe, which I don't read. A Riemann example is, well, I mean, what is supposedly a Riemann example is known. It's essentially something like, it doesn't have a lacunar series, and it has something which barely converges at the level of C0, so something like, I don't know, 1 over n log square n, and then sine nx, for instance. And of course, you would expect that that one is not differentiable, but there are some strange points at which it is.
Yeah. Sorry, I'm not a mathematician. I apologize in advance if this is a naive question, but is there a connection between these non-differentiable functions everywhere and non-measurable?
Non-measurable function, well, I shouldn't be so categorical. Not that I know of. So non-measurable functions need the axiom of choice to be proven to exist, which was one of the reasons, like Lebesgue said, maybe we don't take the axiom of choice. No, these ones, they don't need the axiom of choice. See, like, for instance, this thing that I have produced is out of an actual iteration, which, I mean, I can do everything with sort of, countable things. So I don't need the version of the axiom of choice, which is more complicated.
Sorry, I was wondering, like, the derivative of one of the sequences in Weierstrass function, like the truncated Fourier expression.
Right. You truncate?
Take the derivative of
yes.
any of those functions.
Yes.
And that's going to basically be something that, it's not going to converge to something that
so it's not going to converge to a function. Well, of course, it will converge to an ugly distribution if you want to make sense in the sense of distribution. So you have a way of making sense of what that limit is. It leaves the realm of function completely, but it doesn't land you on something as pathological as, say, non-measurable function, which you wouldn't see out of any sensible approximation mechanism which starts with finite and goes over, like, countable number of iterations, right? So, I mean, when you start with something nice and you make a countable number of iterations, you always end up into something which is measurable. In fact, you end up into something which is Borel measurable, which is even much better.
If we have no other questions, thank you for a fascinating tour.